Let's take this previous JEE Advanced question. It says for every twice differentiable function fr maps to minus 2 comma 2. So the codomain of the function is minus 2 to 2. With f0 square plus f dash 0 square equal to 85, which of the following statement is or are true? First option is there exists r comma s belongs to the real domain where r is less than s such that f is 1 1 on the open interval r comma s. Now here you see, can the function be a constant function? That first we need to justify. Is it possible, say for option A, is it possible that f dash x is equal to 0 for all x belongs to the domain that is the set of real number? Is it possible that the derivative is always 0? If derivative is always 0 for every real value of x, then that implies f dash 0 should be equal to 0, and f dash 0 equal to 0 implies here if this quantity is 0, then f0 square will be equal to 85, and that will imply f0 value has to be either root 85 or the value should be minus root 85, which is approximately 9 point some value or minus 9 point some value. So of course that is not within the codomain. Codomain is restricted to minus 2 to 2. That means that f dash 0 cannot be 0. F dash 0 cannot be 0. Clear? Because then f0 cannot be these two values. So that means it is clear that the derivative cannot be always 0 for every real values of x. So it is not a constant function. It is twice differentiable function, but it cannot be a constant function. So if it is not a constant function, that means sometime there should be at least a one subinterval in the real domain where the function should be having a positive derivative or a negative derivative, because the derivative cannot be always 0. So sometime there should be at least one subinterval where the derivative will be positive. That is, the graph will be something like this. Derivative is positive in that subinterval r to s. Or there will be a subinterval for the function where the derivative will be negative. Function will be decreasing for r from r to s. So there must be a subinterval r comma s where either the derivative is positive, here derivative is positive, or the derivative will be negative. So automatically in that subinterval, since function is twice differentiable and derivative is positive, function is increasing. So here the function will become 1 1. Similarly here function is decreasing, so function will become 1 1 function, injective function. So first option is correct. First option is correct. Next, if we come to option number C, option number C says that in every situation limit extends to infinity fx should be equal to 1. Okay, this one we need to justify that for all such differentiable functions satisfying this condition, limiting value at infinity is always going to be 1. This one also, if we take an example, say fx is equal to sine of root 85x. If you take this function, fx equal to sine of root 85x, we got the idea of root 85 from here. Okay, so for this function, what is the function value at 0? f0 is equal to 0, and if we go for the derivative f dash x, so that will be root 85 into cosine of root 85x. This is the derivative. What is f dash 0? F dash 0 will be, if we put x equal to 0, it will be root 85 into 1, that is root 85. So it is satisfying the condition. You see, the condition is f dash 0, f0 square, that is 0 square, plus f dash 0 square, that is root 85 square, is equal to 85. So this function is satisfying all the possible conditions given here. Okay, but for this particular function, it is a periodic function, sine function. At infinity, the function will just oscillate between minus 1 and 1 without any tendency. So limit extends to infinity for this function does not exist. So we cannot say that for all such functions the limiting value has to be 1. That is a wrong statement, because for this example the limit does not exist at infinity. So option C is not correct. Option C is not correct. Next, let us check option B. Option B is there exists x naught between minus 4 to 0 such that mod f dash x naught is less than equal to 1. Since function is twice differentiable, so it must be continuous and differentiable. So applying LMVT, apply Lagrange's mean value theorem in the interval minus 4 comma 0, we can say that there exists a x naught between minus 4 comma 0 such that f dash x naught should be equal to f of 0 minus f of minus 4 divided by 0 minus minus 4. I am using Lagrange's mean value theorem in the domain minus 4 to 0. So as per the Lagrange's mean value theorem, there exists x naught in the domain for which this should hold. So mod f dash 0, mod f dash x naught x0 is equal to mod of f0 minus f of minus 4 divided by 4. Okay. And mod of a minus b, this is less than equal to, what is the maximum value of this quantity? This is less than equal to mod f0 plus mod f of minus 4 using modular inequality. We can include the minus inside also, no problem. Mod f0 plus mod of minus f of minus 4. And what is the maximum value of mod f0? As per the codomain, maximum value is 2. This one maximum value is 2 and this one also maximum value is 2. So it is less than equal to 2 plus 2 by 4, that is equal to 1. Okay. Maximum value of mod f0 will be 2 and mod of minus of f of minus 4, that is same as f of minus 4 mod, that is also going to be 2 because the codomain is minus 2 to 2, range will be subset of codomain. So this value maximum 2, this value maximum 2, so this is less than equal to 1. So option B is correct. Okay. So option B is correct, and similar to option B, you see, we can say that applying, there will exist an x1 between 0 to 4, there will exist a x1 between 0 to 4 such that, again applying Lagrange's mean value theorem, f dash x1 should be equal to f4 minus f0 divided by 4 minus 0, and if you apply modulus, it will be like this. So this is equal to mod of f4 minus f0 divided by 4, and this value will be less than equal to mod of f4 plus mod of minus f0 by 4, and this value again will be less than equal to 2, and this value again will be less than equal to 2. 2 plus 2 by 4, so that is 1. Okay. So similarly, as for this option between minus 4 to 0, this condition will hold, and we can extend the definition between 0 to 4 also, there will exist at least one x1, so that mod f dash x1 is less than equal to 1, right? Now, for that, this option D we are going to test. For option D, let us consider a function. Capital Fx is equal to, getting the inspiration from here, capital Fx is f square x plus f dash x square. In this model, let us choose a function. Okay. This is suppose capital Fx. What is given in the question? In the question it is given capital F0 is equal to 85. This is given to us. Okay. And this is the function. Now let us analyze. You see that we got one x0 between minus 4 to 0. So if I substitute that, f of x0, so that will be equal to f square x0 plus f dash x0 square. Okay, x0 is between minus 4 to 0, that we have already proved. So f square x0, what is the maximum value? F square x0 maximum value, fx0 maximum value is 2. So this one maximum value will be 2 square, and f dash x0 maximum value is what? Mod f dash x0 is less than equal to 1. If we square both sides, you will get f dash x0 square is less than equal to 1. Just squaring both sides, so it will be 1. So it is equal to 5. So capital F x0 is less than equal to 5. Similarly, here we got one x1 between 0 to 4. So if I put that here, f of x1, that will be f square x1 plus f dash x1 square. And this is also going to be less than equal to, this value is going to be less than equal to 4, less than equal to 4, same logic. And this value is also going to be less than equal to 1 squaring. So this is also less than equal to 5. Okay. So try to analyze how this graph is going to look like, how this particular function is going to look like. So this particular function is going to look something like this. X0 is somewhere here between -4 to 0 and x1 is somewhere here between 0 and 4. At x0, the function value is less than equal to 5. This is the value, say f of x0. This is less than equal to 5. And f of x1 is also less than equal to 5. Say f of x1 is somewhere here. F of x1, that is also less than equal to 5. That is less than equal to 5. But as per this condition, f0 is equal to 85. f0 is equal to 85. So at 0, the function fx is giving a value which is 85. That is, say somewhere here 85. And this value is less than equal to 5. This value is less than equal to 5. So we can get an idea that function, this function capital Fx is starting from a value less than equal to 5, say here. It is going to 85 and then again coming down to something less than equal to 5. So definitely there must be a local maxima either at 0 or somewhere else, right? There must be a local maxima either at 0 or it will be a local maxima at some other point, say it is at, say, alpha. It is at alpha. At alpha, a local maxima will be achieved. So at the local maxima point, the derivative must be equal to 0. Derivative must be equal to 0 at the local maxima point. So for this function, there must be a local maxima where the slope should be 0, because function is starting from here, then reaches the maxima, then again it will fall down. So here at the maxima point, the slope should be 0. So capital F dash alpha will be 2f alpha into f dash alpha plus 2f dash alpha into f double dash alpha. So we can say this for some alpha between -4 to 4. Between -4 to 4, there should be some alpha. That alpha may be 0 also or any other value. So now here you see that if I take 2f dash alpha common, we will get f alpha plus, so this should be 0. This should be 0. F dash alpha should be 0 for some alpha. So 2f dash alpha common, f alpha plus f double dash alpha, this should be equal to 0. Clear? Now out of these two factors, which one can be 0? Can f dash alpha be 0? Can f dash alpha be 0? See, if f dash alpha is 0, what will happen? If f dash alpha is 0, then what is going to happen? We have got product of two factors which is 0. If f dash alpha is equal to 0, that implies what is the function value at alpha? F of alpha. F of alpha will be f square alpha plus f dash square f dash alpha square. This is the value of the function at that point. So we are talking about this function value. Now f square alpha is less than equal to 4 as per the definition. F square alpha is less than equal to 4 and f dash alpha is 0 as per our assumption. If f dash alpha is 0. So this value is less than equal to 4. But as per our assumption, this value is the maxima. So this value should be either 85 or more than 85. This value should be either 85 or more than 85 because it is a local maximum. But something which is less than equal to 4 cannot be greater than or equal to 85. It is not possible that this value will be greater than or equal to 85 because it is already less than equal to 4. That means that this factor cannot be 0. If this factor cannot be 0, that means this factor definitely should be equal to 0. This factor must be 0 because the product is 0. So option D is, there exists alpha between -4 to 4 such that this factor, the second factor is 0, but f dash alpha is not 0. So option D is correct.